field due to electric current.
Students, today we have to find out the magnetic force on a wire carrying a current. But before that, all of you know that the Lorentz force equation. We know that Lorentz equation. Which one? That is F, which is equal to the charge into the electric field intensity plus charge into the what we get there V cross B. Right? In that, this will be the electrostatic force acting on the charged particle, and now this will be the magnetic force acting on the charged particle. Right? Now, from that, we want to take the, or we want to find out the force acting on the conductor inside the magnetic field. But for that, here we want to see the two different cases. That is the first one. That is the shape of the conductor is that is the straight conductor, and second one is the arbitrary conductor. So we want to find out the force acting on a straight conductor. So we want to see the first case. That is which conductor? That is the straight conductor. For that, first of here, we want to take the one of the straight conductor. Suppose here, if we consider this is the straight conductor. The length of this conductor is suppose there L. Right? And again, this conductor which is placed inside the external magnetic field. Suppose here if we consider this will be the magnetic field, and you know the meaning of circle, and inside the circle we take the dot. So meaning of that one is here the magnetic field is present, but this magnetic field is perpendicular to the plane of the figure, and again which is moved away, that is in outward direction. Right? Now this will be the meaning of the circle and dot. So this will be the presence of external magnetic field. Here, the magnetic induction of this magnetic field is supposed to be. Here, the current is going to this conductor is along this direction. Now this is the direction of current. Right? And we know that if this will be the direction of flow of current, then the direction of motion of a charged particle, that is electron, is opposite to this current. It means that here in this, here the number of electrons are present, and that electrons which is moves along this direction. Now this is the electron which is moves along this direction. Here this electron is nothing but the charged particle. Right? Instead of this electron, we take their charge also, that is the Q also. Right? And again, here the charged particle, that is this electron, which is moves with the velocity is Vd. Vd is nothing but the drift velocity. Right? So here we get the mainly three quantities. First one is the current. Right? Second one is the magnetic field. And now third one is their force. Right? So here we want to find out the direction of the force. So for that here we want to use the left hand rule. Here, first of here, the first finger represents the direction of magnetic field. Then Middle finger indicates the direction of flow of current. Then outstretched thumb indicates the direction of force acting on that charged particle or simply conductor. Right? Now here we want to represent this one. So what is it there? Here we want to show these three quantities. So what is it there? First of here, this will be the direction of current. This will be the direction of force. And now here, this will be the direction of magnetic field. Which one? This will be the direction of current. Now this will be the direction of force, and now this will be the direction of magnetic field. Right? Then now here, first of you, we want to write down the force acting on the charged particle or this conductor. Right? So what is it there? Magnetic force. Equation of magnetic force. We know that the magnetic force acting on a conductor or charged particle, acting on a charged particle. What is it there? What is the equation? The equation is Fm, which is equal to the Q into the V cross V. Right? And you know that the direction of drift velocity is opposite to the current. It means that this will be the direction of the drift velocity. Right? Now this will be the drift velocity. Right? Suppose this will be the equation number 1. But before that, we know the definition of the current. What is it there? But what is it there? I, which is equal to the I is nothing but the charge per unit time. It means that here instead of I we write down the charge per unit time. It means that charge per unit time is nothing but the current, or the rate of flow of charges is nothing but the current. So here we write that current I, which is equal to the Q upon T. Here T is the time which is required for to cover the distance in the L, that is length of the conductor. And now in here, suppose that if we consider this is the one of the plane. Suppose that this is the plane is P, and now this is the P dash. P dash represents the one of the plane. Across this plane, this charges which is moved. Right? So this will be the I, which is equal to the Q upon T. So what is it there? Therefore, Q, which is equal to the I into the T. Suppose this will be the equation number 2. Now we want to substitute this value. But before that here, we want to again substitute the value of small t. We know the formula of simply velocity. Velocity is nothing but the, what is it there? Displacement upon time. So in terms of the magnitude, what is it there? Distance upon time is nothing but the velocity. So here what is it there? So V, which is equal to, that is the drift velocity, which is equal to the distance. Here distance is L. So what is it there? L upon time. Time is there T. So what is it there? T, which is equal to the, what is it there? L upon simply V. Now we want to again substitute this value in this equation. So what is it there? Therefore Q, which is equal to the, here I is as it is, and the value of small t is, what is it there? L upon their drift velocity. Right? Suppose this will be the equation number 3. Now put equation 3 in equation number 1. What is it there? See here. Now substitute this value here. So what is it there? Fm, which is equal to the, what is it there? Fm, which is equal to the, instead of the charge, we want to write down I L upon Vd. Right? Inside the bracket, what is it there? Vd cross vector V. Now in here, we want to write down this one in terms of the vector. Here, cross product. Here, that cross product which is represented by the sin theta. So what you get there? So here, Fm, which is equal to I L upon Vd into the Vd being sin theta into the, now here, unit vector. Suppose that if you take the unit vector is n. Here, the direction of this unit vector is along the force. Right? It means that perpendicular to the plane in which velocity of the charged particle and magnetic field is present. Right? So here, what you get there, this Vd get cancelled. So what you get there? Fm, which is equal to this R is as it is, L is as it is, D is as it is, and now here what you get there, sin theta into the n cap. Right? Again here, suppose if you want to write down in terms of the cross product, then what you get there? Fn, which is equal to here R is as it is, here L and B. Again, L is the length vector and B is the magnetic field. So here we write down L cross vector B. Instead of sin theta and unit vector, we simply use the cross sign. So what we get there? Fn, which is equal to the R into the L cross B. Right? So this is about the force acting on the conductor or charged particles inside the external magnetic field. Right? Now again here we want to see the different case. Right? Now here case 1. A. What we get there? A. Now here we want to take this one. A. The angle between the L and B is 90. Then what we get there? If theta which is equal to the 90 degree, then what we get there? Then sin 90 which is equal to the 1. Now substitute this one in terms of the magnitude. So Fm which is equal to the simply R L B, and this will be the maximum force which is acting on the charged particle or simply conductor. But suppose here, if we consider the angle between the L and B is 0. It means that here, if we place this conductor along the direction of external magnetic field, then what we get here? Now, second case. A, the value of theta which is equal to the 0, then sin 0 is 0, then at that time the force acting on that charged particle or that conductor is 0. Right? Now, this is about the different case, that is the force acting on a charged particle or conductor inside the external magnetic field. See all the equations once.